Hello friends, in this video I will try to explain the logic behind the solution of the problem 2749 of lead code minimum operations to make the integer 0. First, what I heard about this problem is from this group code in beTounsi, where its owner put it in his Facebook group. Also, he has a YouTube channel, called Code beTounsi. It's a very helpful channel. I learn a lot from that channel. Well, I give him my first idea or my first logic. Well, I'm going to explain in a moment. Let's see the problem statement first. It says you are given two integers, num1 and num2. In one operation, you can choose integer I in the range 60 inclusive and subtract 2 power I plus num2 from num1. Return the integer denoting the minimum number of operations needed to make num1 equal to 0. If it is impossible to make num1 equal to 0, return -1. As you see here in this example, gives me num1 3, num2 -2, output is 3. 3 because the minimum operation to make 3 0 following this principle. First, if I take I is equal to 2 and subtract 2 power 2 plus -2 from 3, you will get this expression. 3 minus 2 power 2 is 4 plus -2 is equal to 1. Then I take I is equal to 2 one more time to subtract 2 power 2 plus -2 from 1, this one. It will be equal to -1. And then we choose I is equal to 0 to subtract 2 power 0 plus -2 from -1, then we get 0. So we need the 3 operations to make 3 equal to 0 following this principle. For 5 and 7, there is it's impossible to do this, so that's why here we have -1. Here the constraints. We have num1 from 1 to 2 power 9 and num2 from -10 power 9 to 10 power 9 inclusive. Maybe if you are going to try this problem, we're going to stack, or at least you will think like I taught here, using this logic. But here for this solution is a little bit different from this one, but it has the same idea in deep. They have the same principle, the same logic. Let's see it together. Let's first understand the problem. How we're going to work here. If I have two numbers and one, let's call it n1 is equal to 3 and 2 is equal to -2, and I will take here the powers from 0 to 3 to make the description shorter as possible, and we will compute a number a, which is equal to n1 minus 2 power I 1 plus n2. And then I will be going to compute b, which is equal to a minus 2 power I2, because the power could be different here, equal here, but it could be different, plus n2. Then c to a is equal to b minus 2 I3, the power I3 plus n2, and etc. until to reach 0. We will count the number of steps to reach 0. Let's take this example. First, I will compute A for all the powers. For 0, using this formula, of course, for the power I, 0 is equal to 0, so A will be 4. For the power 1, A will be 3, for 2 will be 1, A, and 3 will be minus 3. Then, I will compute for each A, I will compute B. For A is equal to 4, I will use this formula here. This one. For each A, I will compute B for the same powers from 0 to 3. For A is equal to 4, B, it could be for power equal to 0, it would be 5. Power is equal to 1, 4, B. And power is equal to 2, we have 2, and 3, we have minus 2. For A is equal to 3, this one here, A is equal to 3. B will be 4, 3, 1 minus 3 for each power. For A is equal to 1, B will be 2, 1 minus 1 minus 5. For A is equal to minus 3, B will be minus 2 minus 3 minus 5 minus 9. We don't reach 0 here, so we'll continue. We compute C, this one, using B, all the B's here. Okay. For B is equal to 5, we have C is equal to 6 for the power 0, here, power 0. B is equal to 6. For B equals to 5, C is equal to 6. For 5, for power 0. For power is equal to 1, C is equal to 5, etc. 2, C is equal to 3. 3, C is equal to minus 1. For B, for all B equal to 5. If B is equal to 4, for B equal to 4, this one. Sorry, here. So we have all these C's. For B is equal to 2, we have C. For each power, we have this results. As you see here, we reach 0. So we can stop here. How many operations we have done here? We have 3 operations. We compute A, then B, then C. We have 3 operations. Okay. On the C's and for this B, we have no 0. Then this result, sorry, is for this column of B's. Now we compute all the C's for this all these B's. We have B is equal to 4. We have this result for all these powers. C for B equal to 3. For B is equal to 1. We have all these. And B equal to minus 3. We have no 0. Here we have this B's. We compute for B is equal to 2. We have all these results for all these powers. So we have one more 0. So we can say that we have 3 steps. Also, we have compute A, B, and C. And here we have no 0. Here we have this 0. As you see, we can find multiple results. But when we code the problem, we going to do all the stuff because it will. First, we don't know how many steps. Then it could be this is the brute force approach. The time complexity it will be very big. I don't know how to. I didn't code it because it will take much time. The time complexity it will be very, very great. very big. So the logic, first, you have to think like this, as I did when I respond in comments from code in beTounsi. First, we can say that first we're going to compute A is equal to n1 minus 2 power I1 plus n2. Then B, as we see, C, and D until reaching 0. We have k steps here. So we can say, we can substitute each variable by its own expression. For example, here I can substitute C here, this C, I can substitute it by this one. We have B, then B, we have B by this one, and A by this one. So and at the end, I will find this one, this expression. A is equal to n1 minus 2i1 plus n2 minus 2 power i2 plus n2 minus 2 power i3, etc. K. How many times this expression will be equal to 0? How many times here we have k steps? Okay, so this is the easy math now. We can say that n1 minus k multiply times n2 because we have k steps here for n2 minus all these powers equal to 0. How many power we have there? Yes, exactly, we have k powers of 2. So we can say that this sum of k powers of 2 is equal to n1 minus k times n2. So we have that sum, let's call it S, is equal to n1 k times n2. But we have to be careful here. As we have seen here, this how many power of 2 here, or powers of 2, we must have k. Okay, because we have the same k here from this one. So if S contains k powers of 2, return that k, otherwise return minus 1. Using this logic, we can say this. This obvious here, it does make sense. Okay, let's see the first pseudocode. I'm going to, for example, to make k going from 0 to 1000. I could compute S. S is equal to n1 minus k times n2 for each k. Now, if k powers of 2, if it has k powers of 2, which is if S has k powers of 2, I will give this a function. It will return true if S has k powers of 2. It will return false and otherwise. So it will give us parameters here S and k. We're going to return k. If k is not returned, if the end of the loop, return minus 1. So that function, it will check if an integer has k power is 2. So we're going to reduce the problem we're going to reduce the problem to this one. So we're going to check if an integer has k power of 2. This is a well-known problem. Frankly, I didn't know the code at this time. I found the code in Geeks for Geeks. Let's see it together. Okay. So of course here, to check if an integer n has k powers of 2, we have k must be at most equal to n. It does not make sense if k is greater than n, because at most we can write n using n power of 2, which is like 9, for example. Here 9, it could contain 9 powers of 2, which is 2 power 0 plus 2 power 0, 9 times, as you see in the presentation. This is the explanation in Geeks for Geeks. This is the code. I will explain it. How they come to this code. Then let's call x as the number of set bits in n. So x is the number of the powers of 2 that represent the decimal representation of n. You know that. It does not make sense that x is greater than k. Why? Let's take an example here. 14 in the decimal representation is equal to 110 in the binary representation. This is what we have learned in the school. Okay. So we can write 14 is equal to 2 power 3, 2 plus 2 power 2 plus 2 power 1. So 14 could be represented at least by the summation of the 3 powers of 2. So k must be greater or equal to 3. We cannot find k is equal to 2 or 1 for 14 or 0. Okay? At least 14 could be represented by 3 and 4, or a number greater than 3 to represent 14 as the sum of the powers of 2. Okay. So if x is equal to the number of the set bits of n, so if x is greater than k, as we have seen, or k is greater than n, so we return false in this case. We don't need to continue. You may be tell me if what for 8? For 8 here is equal to 2 power 3. So the binary representation of 8 is, I think, this one. 1, 2, 3. So x is equal to 1. So k, it could be greater or equal to 1. You cannot represent 8 by 0 powers of 2. Okay? We can find the number of set bits in C++ in constant time. I don't know for the other languages like Python or Java. I don't know it. You can Google it. But in C++, we can find it on constant time. It's cool. Okay. From where we start checking the powers now? If you have a number n, from where I will check the powers? Which is, the answer is the greatest power of n. It's very obvious. It makes sense. Let's see it together. If n is equal to 2 max power, so max power is equal to the floor of log 2 by n. Okay, log base 2 of n. Let's take an example of if n is equal to 9, the max power is log base 2 of 3, which is equal to 3. For 14 equal to 3 also. For 100 for 29, the max power is log base 2 of 129, which is 7. Because as you see here, the binary representation of 129 is this one. 0, 1, 2, 3, 4, 5, 6, 7. So this is the max power of 2 that we have in the 129. We can make it in Constantine also in C++. How to know if a power of 2, for example 2 power I, is a part of the sum of the k powers of 2. This is the tricky part now. Let's take this example. N is equal to 9 and k is equal to 3. So you want to make 9 is the sum of 3 powers, exactly the sum of exactly 3 powers of 2. So we can say that 9 is equal to 2 power 2 plus 2 power 2 plus 2 power 0. Okay. If I want to check, is 2 power 3 is a part of the sum? No. Is 2 power 2 is a part of the sum? Yes. You say what we say here. We have nothing. We know that. It makes sense. It makes sense. This one, I will check for this one. If n is equal to 129, k is equal to 6. Let's see the let's observe this. We have an observation here. Let's see what we have. Of course, this one is not mine. It's from this. From Geeks. Geeks for Geeks. Sorry, this one. This relation here. Let's see it together. So, if I subtract from 129 2 power 6. It will leave me with the sum which is equal to 2 power 5 plus 2 power 4 plus 2 power 3, 2 power 3 plus 2 power 0, which is greater than 6 minus 1. 6 is the number is k, number of powers I want to make the sum with it. Let's continue. If 2 power 6 is a part, so I can reduce it from n. Okay. So I will have 65. 65, I will reduce the greatest power here, which is 2 power 5. I will leave me with the same 2 power 4, 2 power 3, 2 power 3, 2 power 0. Is greater than 5 minus 1. Why 5? Because I have used 1 here. This one. You can say y minus 1 here. Minus 1 because, sorry, y minus 1 for 6 here because I used this one. That's why, because it's minus 1. Same here. So it will leave me with 5 now because this is used. Now I will check 65. The number of 5 powers of 2 for 65. Because we do not talk about 6 here. 6 is for 129. When I found 1 power of 2 for 129, so we have to reduce k by 1 because we found 1. So it will leave me with 65 minus 2 power 5. The same observation here is the sum is greater than 5 minus 1. Okay. So now I will reduce n from n to power 5. It will give me 33. So I will check this power now. 33 minus 2 power 4 is equal to 2 power 3, 2 power 3 plus 2 power 8, which is greater than 4 minus 1. 17 minus 2 power 3 is equal to 2 power 3 plus 2 power 0 is greater to 3 minus 1. Okay. 9 minus 2 power 3 is equal to 2 power 0, which is 1, is equal to 2 minus 1, which is 1, greater or equal now. Okay. And 1 minus 2 power 0 is greater or equal to 1 minus 1. 0 is equal greater or equal to 0. All this relation are true. So from this observation, we can say if I have 2 n minus 2 power I is greater or equal to k minus 1. So this power is in the part of the sum. Let's say it more precisely here. The same example, but here I will compute the greatest power. Like base 2 of 129 is equal to 7. So I will check if 2 power 7 is a part of the sum of the exactly 6 power of 2 of 129. I will make the integration, Boolean expression here is 129 minus 2 power 7 is greater or equal to 6 minus 1, which means is 1 is greater or equal to 5. The answer is no. So we will continue to the previous power. The maximum power we have computed here, so we're going to 6 here, the previous power. We check the same. Is 2 power 6 is a part of the sum of the exactly 6 power 2 of 129. 129 minus 2 power 6 is greater or equal to 6 minus 1. So is 65 is greater or equal to 5? The answer is yes. So we can say that 2 power 6 is a part of the sum. And we have to recompute n, because now for 129 we have found a power of 2. So we will get 129 minus 2 power 6 is 65, and k will be reduced to 5. Why? Because we're going to check if 2 power 6, the same power, is a part of now exactly 5 power as 2, but is not for 125, but for 65. Okay? This makes sense. You have found a power for 129. So we have found a power. So we have found 1. We are going to find the 5 other 5 powers. Is 65 minus 2 power 6 is greater or equal to 5 minus 1? Is 1 is greater to 4? The answer is no. So we go to the previous power, which is 4. Which is 5, sorry. 2 power 4. Check if 2 power 5 is a part of the sum of exactly 5 power 2 of 65. Compute 65 minus 2 power 5 is greater or equal to 5 minus 1. Which is 23 is greater or equal to 4. The answer is yes. 2 power 5 is a part of the sum. So we can recompute n and we reduce k, because we have found 2 powers now. 2 power 6 and 2 power 5. But it remains 4 powers. We're going to check these 4 powers and the rest of n we have found, which is 33. Check if 2 power 5 is a part of the summation of exactly 4 powers of 2 of 33. We reduce 2 power 5 from 33 is equal to 4 minus 1. 1 is greater or equal to 3. Answer is no. Go to the previous power, which is 4. Is 2 power 4 is a part of the summation of exactly 4 powers of 2 of 33. 33 minus 2 power 4 is greater or equal to 4 minus 1. Is 17 a greater or equal to 3? The answer is yes. We have found the power. 2 power 4 is a part of the sum. Compute n and reduce k. So we have found 3 powers now, and it remains 3. Same for 2 power 4 in 17. The answer is no. We go to the previous power. Same 2 power 3 in 17. The answer is yes here, as you see in the expression. So we have to find another power. So we have to find 2 or 4 powers now. It remains 2. So we're going to check the 2 other powers in 9. Check if 2 power 3 is the part of 9. Of course, yes, here, because 9 minus 2 power 3 is greater or equal to 2 minus 1. 1 greater or equal to 1. The answer is yes. So 2 power 3 is a part of the sum. We compute n is equal to 1. It remains 1 power. Check if it is 2 power 3. The answer is no. check if it is 2 power 2, the answer is no 2 because 1 n is equal to 1. Last one, the last power here, or n is equal to 1. 1 minus 2 power 2 is greater than 0. And answer, of course, minus 3 is not greater than 0. Go to the next power, which is 1. 2 power 1 is it the part of the sum of 2 of 1? The answer is no here also. Let's go to the previous power. So we go to check. Is 2 power 0 is a part? The answer is yes. So we compute n, we compute k. So we have k is equal to 0. We have found all the powers. So we can say that n is equal to 2 power 6, 2 power 5, 2 power 4, 2 power 0. Of course, you can say we have another possibilities of to find 6 powers of 2 for 129. The answer is yes, we can find. But here, we have to find. We just find 1, 2, turn 2 using this technique. So the general formula here we can say if n minus 2 power I is greater or equal to k minus 1, so we can say that 2 power I is a part of the sum of exactly k powers of 2 of n. We have to prove this mathematically. We have to prove this, but to be honest with you guys, I didn't figure out how. I tried lots of techniques to demonstrate this. But mathematically, I didn't figure out how to prove this formula, the correctness of this formula in general, of course. If you found a way, guys, let me know in the comments, please. So we can write the pseudocode of this code. The first we have, as you have seen earlier in this presentation, we have to go number of the steps k from 0 to 1000, compute the sum, check if that sum contains k powers of 2. If yes, return k. Otherwise, we're going to, if we end all these steps, we return minus 1. Maybe you ask why 1000 here. Just guessing here, guys. I don't know. Because I just say the number of steps, I choose 1000. It could be great. It couldn't be greater for 1000. Now the function. Now our function has a k powers of 2. It will take as parameters the integer n and the number of powers that we have to find. First, we compute the number of set bits in n. X is equal to the number of set bits in n. We can do it in constant time. As we have seen earlier in the presentation, if k is greater than n or x, which is the number of set bits, is greater than k, we return false. Otherwise, we continue. We compute the max power of n, max power of 2 of n. We can do it at the time in C++, and we're going to compute while I is greater or equal to 0 and k is greater than 0. If k is equal to 0, so we have find all the power, or we stop if we reach the power is equal to 0, less than 0. So okay, we compute the power 2 power I. And we check our formula. If n minus that power, 2 power I, is less than k minus 1, so we go to the previous power and we continue. Otherwise, we reduce k, we reduce n, and we'll continue that until reaching k equal to 0 or I is less than 0. Okay, then we return true. So this the time complexity of this code is O big O1000 for this one, and you can say that log O log base 2n for this function. But here, as you see in the constraint of the problem, n could be the maximum n 10 power 9. So we can compute directly here. Log base 2 of n is almost 30. Sorry. So we can say that the maximum, the overall time complexity is O 1000 plus O 30 is equal in test times. You can do it with this. This is the code in the code. It works. As you see in C++, we can use this function to compute the number of set bits of an integer n, and we can use this function to compute exactly the log base 2 of n. It gives me return the floor, the integer. We can do it in constant time too, but you have to be careful here of the types. We use this function built in CLDLL because n is the long type, data type. Same for pub count LL. N is the long LL. We have to be careful also in this computation of S, because we have k is an integer and s it could be long. We have to cast k to long too. Okay. This trick will give me this trick. I knew this trick from code in beTounsi. Would correct me here in his comment. Thanks to him. Also, this computation of log base 2 is from code force. You can see it here in this block. Okay. But if you pay attention here, if you pay attention in the code, you see here, if this is return false here, or this one expression, or directly return true here. This computation, we have no return. So, if we pass from here, it will compute this one and return true. We can omit all this and say this code. We compute the number of set bits of n, of s here, and we say the inverse here. If k is greater or equal than x, and k is less or equal than n, return true. Return k, sorry. Then for this function, otherwise, if k is not returned, then when you finish all the steps, return -1. It's the same code here as you see, because we have a return here for this code. We return k when this is true. Okay. So to be this is true, first we have to pass here, to pass this expression. So if this expression is true, we can return true. The inverse expression is true, we return k, as you see here. This is how the guys, I think, come to this code. If you have more questions, guys, let me know in the comments. I will answer immediately. Thank you for watching.